In chemistry, we deal a lot with really big and really small numbers. So what I want to do in this section is just do a very quick review of scientific notation and also go back over the terms mass and weight and make sure you understand the difference. So scientific notation is whenever we have something based on the powers of 10. So everything's in multiples of 10, and we're going to express that multiple as an exponent. So you would have some sort of a base number, and for us that base number is going to be 10, and then it's going to be raised to some exponent. That exponent goes up top. That exponent tells us how many zeros we're going to have. For instance, we could talk about 1 atom of gold. 1 atom of gold has a diameter, so all the way across, of 3 times 10 to the negative 8th centimeters. Is that big or small? And it has a mass of 3.3 times 10 to the negative 22nd grams. Okay, is that big or small? So a lot of times students will come in saying, oh, you move the decimal to the right or to the left, but then they get confused on if it's to the right or to the left. So this is how I remember it. This is a negative number. This is a negative exponent. If they're negative exponents, they're really small. It's 0.00, however many zeros that you need to have in there. And this negative 8 means that we have to move the decimal place 8 times. Negative 22, well, that's an even smaller number. We had to move the decimal 22 times to make it a really, really, really small number. So big numbers have positive exponents, small numbers have negative exponents. Down on the bottom, we have some different examples. This is showing different exponents. So I'm actually going to add one. Have you ever thought if you have a 10 to the 0 power, what does 10 to the 0 power mean? So if you had 1 times 10 to the 0 power, well, that means that you have no zeros. That's just 1. Yeah. Right here we have 1 times 10 to the first power. That's 10. And then they're representing that 10 with 10 little dots. Next we have 10 to the second power, or 1 times 10 to the second power. That means that we have 100. If it's 10 to the third power, we put 3 zeros. That's 1,000. It's showing us how many places we're going to move that decimal. Now, look over here at the other side. It says 2 times 10 to the first. Remember, 10 to the first was 10. And then we're going to multiply that by 2. That gives us 20. So go to the next slide. We'll do a few questions and then see how it goes. So here's a few problems for you. If you need to, pause the video, try them out, and then we'll go over the answers. Now on the test, you would be responsible for being able to convert to scientific notation and then going from scientific notation back to longhand. It's just good things to be able to know how to do. So let's look at this first part. Convert the following to scientific notation. Well, the first number is a really, really big number. That means we're going to have a positive exponent. When we look to figure out where we're going to put the decimal point, the decimal point is going to go, I'm going to change my ink color here, right after your first non-zero number. So it's going to go right after that 4. So I'm going to put 5.04. You might say, well, how do I know how many decimals to go out then? There's a lot of rules associated with it. Not all of them are applicable for this class. My general rule of thumb, you're going to keep going until you've written down everything that's not a 0. If it's just zeros after that, we're going to use the scientific notation to give us an idea of the size. All right, so I have 5.04 times 10. Well, let's see how many places we move that. It is right here right now. And then we're going to move it to where that little top hat thingamajig is. So we have 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th. And that is a positive 7 because, again, it's a big number. All right, the next one. The next one is a tiny number. Now notice it's not a negative number. It's just a tiny number. And because it's a tiny number, a small number, we're going to have a negative exponent. Again, we had to figure out where we're going to put that decimal. We want it after the first non-zero number. That means it's going to be after the 6. 6.7 times 10 to the, we want 1, 2, 3, 4, 5, 6. Negative 6th. So that's a couple of examples on how to write scientific notation. Now let's write it as longhand. The first example that we have, 10 to the 7th. That means it's a big number. That means that we're going to move the decimal place 7 times. Now if you notice, the decimal right now is right between the 1 and the 2. So as we move it around the 2, that's going to count as one of our decimal places. All right, so I have 7 decimal places I'm moving. 1, 2, and then everything else is going to be a 0. 3, 4, 5, 6, 7. Okay. And then you could go back and you could figure out how you would name that in traditional terms. Hundreds, thousands, millions, 12.3 million or 12,300,000. You remember doing that as a kid. Now the one on the bottom, this has a negative exponent. That means it's going to be a really small number. We're going to take the decimal where it's at and we're going to move it to the left. We're going to make this, again, a really, really small number. Now we're going to count from the decimal. I put 1, 2, 3, 4. Now to get around the number 4 we have right here is going to require a decimal place. That's that 5th decimal place that we're going to move. So I can go ahead and put in 4, 3, 2. So 1, 2, 3, 4, 5. I moved it 5 times. Practice a few times. You'll see it being used a lot throughout the semester. Now here's a place where we're actually using that particular idea. Here we're looking at the difference in size between Alaska and Hawaii. Now we know Alaska's a lot larger, but if you look at most maps, it looks like they're about the same size, but we know that that's wrong. So how much bigger is Alaska than Hawaii? Well, on here it gives you the area of each of the states. So Alaska's 1.72 times 10 to the 6th square kilometers, and Hawaii is 2.83 times 10 to the 4th kilometers squared. Well, some people won't actually look at the exponent. They'll just look at the 1.72 versus 2.83 and say, oh my goodness, Hawaii is bigger. Well, we know that's not true. So those exponents really give you an indication of the size of that number. Well, sometimes it's actually kind of nice to write these out longhand. So Alaska, positive 6 for that exponent. We're going to move the decimal 6 places. 1, 2, 3, 4, 5, 6. We'll look to see how to name it. Hundreds, thousands, millions. 1,720,000 square kilometers. That's pretty big. Now let's go down, look at Hawaii. It's times 10 to the 4th. We're going to move it forward places. 1, 2, 3, 4. Hundreds, 28,000. Ooh, there's a lot of difference between 28,000 and 1.7 million. You can do a lot of things looking at those exponents. You can learn how to multiply and divide using them. That's what it's showing in the bottom right. If you have the same base number, in this case we have a base of 10, and we're dividing those, you can actually subtract the exponents. They're done right here, the 6 minus the 4, to give you an idea of the size of that difference. that quotient is kind of fun to play with as you learn some of those rules. Give you a good chance to be able to estimate if your answer is correct or not. The other thing I wanted to discuss was the difference between mass and weight. I'm horrible about using the two terms interchangeably. I know that I am. I know in our society we have a tendency to do that. However, there is a very distinct difference between those two terms. Mass is considered to be the resistance to acceleration. How hard is it to get something started, or how hard is it to slow something down? It's the quantity, the amount of matter. And remember, matter is just stuff. And mass is always the same, no matter where you're at. Sorry about the buzz. That is the clock in my office. Weight, it results from the pull of gravity. So depending on where you're at in the universe, your weight could actually change. It depends on gravitational force. So let's look at an example of this. All right, so here we have some astronauts and a guy pushing a cart. Let's start with the cart over on the right-hand side. With the cart, we have someone pushing an empty cart, and we have someone pushing a cart that is absolutely full. It's my daughter after I shop for her for college this fall. Woo! Now, just looking at those two, which of those two carts would it be easier to start pushing? Well, the one that's empty, that one would be a lot easier. It has less mass. It has less resistance to acceleration. The bigger one has more mass, more resistance to acceleration. It would be harder to get started. Now, once you get them started, assuming you're on a frictionless surface, it's going to be harder to stop the really big one. Now, if you look over at the two astronauts, this is going to show you the difference between mass and weight, another example. Now, both of these astronauts have a mass of 60 grams, or it says 132 pounds. One thing that drives me crazy about this text, it uses both kilograms and pounds when discussing mass and weight. Mass is in kilograms. Pounds is actually the English version of weight. But like I said, in our society, we're really bad about throwing both of those terms out there. So let's go ahead and look at this. The mass, whether that astronaut is on Earth or up on the moon, it's the same. And that's the dinging saying that class is about ready to start, even though it's summertime. So the mass is the same no matter where that astronaut is. The other number is the weight. The weight will change. The weight, if you notice, it says that it's 60 kilograms here on Earth, but only 10 kilograms of weight, again, weight, on the moon. It depends on the gravitational pull. Now, it turns out that gravity, the gravitational pull, depends on the size of the planet that you're standing on. So if you were to go to Jupiter, Jupiter's the biggest planet in our solar system, you would weigh a whole lot more than you do right now, even though your mass would be the same. And then if you travel to Pluto, I know Pluto's not officially a planet anymore, but I really like Pluto. Did you know it was discovered by a Kansan? If you went to Pluto, because it's so small, your mass would be the same, but your weight would change. I always ask some sort of question looking at the difference between mass and weight. Mass stays the same. It doesn't matter if they try to tell you it in kilograms or pounds or whatever. Your weight will change depending on where you're at. Now, the last example that they give is when they're in the space shuttle, and you guys have all seen videos or clips or movies where you have someone in a space shuttle and they're weightless and they can float around. They still have the same mass as they did on Earth or Jupiter or Pluto or Mars or wherever they were at, but their weight is going to change. Mass stay the same, weight going to change. In this case, you're in, they'll call it a microgravity or no gravity. And so their weight will go down to almost zero, and that's how they can float around. My kids watched The Martian the other day. We got to see a lot of that.